this paper from 2017 by Dubovsky, Gorbenko, and Mirabai, and a little bit also from this later paper from 2018. And then the last half hour will be devoted to a more or less independent topic, which is what we can say holographically about these TT-bar deformed theories. Both of these topics are topics that I have not worked on, and I'm not responsible for any of the results that I'm going to describe. And also the authors of these papers, of course, are not responsible for the way that I will present or misrepresent the results. But we'll see how it goes. And please stop me with questions at any time. So I remind you that we heard a lot in Sasha's lectures about these TT star deformed theories, which can essentially be defined by starting from some theory S0, which is a standard quantum field theory, and then doing iterative small deformations around this theory, labeled by some real parameter alpha, involving the determinant of the energy momentum tensor of the theory with the parameter alpha. So this is sort of an iterative definition of the theory, which is rather implicit. And as we saw, it's still very useful. It can be used to compute exact expressions for the energy levels of these theories as a function of alpha, and to compute the S matrix exactly as a function of alpha. So that we already heard a lot about last week. So what I mean by a high energy completion of the TT star deformed theories will be some explicit definition of what this action of the TT bar deformed theories is for a specific value of alpha. So again, this defines it implicitly, but it would be nice to have an explicit expression for the action as a function of alpha. Why would you like to have this? Well, it would be useful to have it to answer many questions about these theories. One question, which is far from obvious from this definition, is what are all the possible observables of these theories? And a related question is, are these theories local? Do they have any local operators in them? In terms of the observables, we know that we can compute these energy levels, and we know that we can compute this S matrix since it has been since they've been computed. But what are all the other observables, or are there any other observables in these theories? What does the theory behave like at high energies? So this deformation by the parameter alpha is irrelevant. So at low energies, the theory reduces to the quantum field theory that we started from. But what do these theories behave like at high energies? And another question you could ask is, can we put these theories on curved space? So of course, if these are standard local quantum field theories, then we can put them on any space that we want. But if they're not local, then it's not obvious on which types of spaces we could compute them. So hopefully, if we have some definition of the theory that makes sense directly for a given fixed parameter alpha, hopefully we should be able to answer these questions. As we'll see, well, I'm not sure if we will be able to answer them, but at least it should help us if we have such a UV completion with which to define the theory. But the question is, how can we find such a description? So of course, we cannot get it directly by solving this equation, because this energy momentum tensor is a complicated function of our original theory. So we have to, more or less try to guess what the answer should be. And an important clue comes from looking at the spectrum of the theory. So again, this was discussed extensively last week. This theory has two different types of behaviors depending on the sign of this parameter alpha. So if alpha is positive, then these theories have complex energy levels, if you just use the exact formulas for the energy levels as a function of alpha. And so they're not unitary. So I won't really discuss this case because I don't understand it. But in the case that alpha is negative, then we saw that these theories do have a sensible spectrum with the real energy levels. And the spectrum is characterized by having a Hagedorn density of states, namely the density of states as a function of energy with some given parameter alpha behaves at high energies compared to the scale set by alpha, and any other scale that we have in this quantum field theory as the exponential of the square root of minus the central charge times alpha times the energy. So here I'm assuming that my original quantum field theory at high energies becomes some conformal field theory of central charge C, which is true for any standard quantum field theory. And then at high energies, you can just read off the density of states from these equations that we saw last week. And again, when alpha is negative, this is some real number. And we have this exponential growth in the spectrum, which, again, as was discussed, is related to the fact that there is some minimal radius on which we can define the theory in a sensible way. So this should give us some clue, perhaps, about the high energy behavior. And so the question is, do we know any theories that have a Hagedorn spectrum? And in fact, we know two types of theories that have a Hagedorn spectrum. Yeah, let's see if I should write this. I'll write it here. So one class of theories that we know that has a Hagedorn spectrum is free string theories. So that's, well, it was one of the original motivations, I guess, for building string theory, is that free string theories have a Hagedorn spectrum. So they're characterized by some string tension 1 over alpha prime. And then if you have a free string theory, then its density of states at high energies goes like the square root of alpha prime times the energy. So when I say free string theory, of course, I don't necessarily mean a free string theory in flat space. I mean, a free string theory can in particular be any large n gauge theory, as we know from Tuft. So there are many different types of free string theories, and one may hope that maybe this theory is a free string theory of some type. Of course, I remind you that if we have a string theory that's not free, then the high energy spectrum is very different, because eventually interactions show up, and string theories involve gravity. So the typical states become black holes, which have a very different density of states. But in free string theories, they do have this property that they share with the TT bar deformed theories of having a Hagedorn spectrum. So one natural guess could be that maybe these theories are free string theories in some sense. Well, this is not perhaps a very useful guess, because, well, there's a huge number of free string theories, and we certainly don't understand how to classify them or what the most general possibility is. But that is certainly one type of behavior that we may expect. The other type of theories that we know which have a Hagedorn spectrum are theories known as little string theories. So these are somewhat mysterious theories for which we also don't have any explicit definition, but we can define them via various indirect ways. So, for instance, one of the places where these theories show up is as the decoupled theory in string theory on K. I mean, this will not be important for the rest of my talk, so if you are not familiar with some of these things, that's fine. But if you look in string theory at a configuration of K Navier-Schwarz firebrains in type 2 string theory, and you take the limit that G string goes to 0, then one can argue that in that limit you get a theory that is decoupled from gravity. It's not gravitational, but on the other hand, it's also not a standard field theory, as can be seen by the fact that it has a Hagedorn density of states at high energies. So this is another class of theories that has this property. And I'm mentioning this class here mostly because this class of theories will actually show up in Amit Givon's talks on Thursday, when he'll discuss a deformation that's closely related to these TT bar deformations. So these would be two natural guesses, perhaps, for what the high energy description of these theories should be. However, we should be a bit careful about what we mean when we say that these theories have a Hagedorn density of states. So this spectrum was computed on a circle of some radius r. And these theories have a Hagedorn density states when they're on a circle. However, if we look at the theories in flat space, so in flat space, as we saw, then if we start from some massive theory that has an S matrix, then in flat space, the S matrix of these theories is actually the same as the original S matrix, just deformed by some phases depending on the momenta. So the spectrum of these theories in flat space is actually not modified compared to the spectrum of the original theory. And you can show that also from these formulas for the deformed energies if you look at states that have a finite energy in the limit that the radius goes to infinity, as would correspond to some particle states. So the flat space spectrum does not have this Hagedorn density of states, but rather it has the usual behavior of particle states in a quantum field theory. And that's, of course, different from what we would get in these theories, which are really essentially string theories, which have a Hagedorn density also for their particle-like states. So it seems that this initial guess, there are theories should be string theories of some type, does not really work. But as we'll see, there is still some way to think of these theories in some sense as a specific sector in a free string theory. But I will not focus on that approach here. So these naive guesses don't work. So the question is, what else can we do to try to define these theories? And to get another clue on how we should perhaps think about these theories, we should notice that there's another way to describe, well, if we think of an infinitesimal deformation of this type, where we take s to s minus alpha over 2 times the integral of the determinant of t, then we can always rewrite this by coupling some matrix h mu nu to t mu nu, and then adding an extra term here, 1 over alpha times the determinant of this matrix h. So this is if you want a Hubbard-Stratanovich way of writing this interaction, so we can always rewrite the interaction, at least at leading order in alpha, in this way by adding these couplings h and then performing the quadratic integral. So h here is a 2 by 2 matrix, so this is just a quadratic path integral, and performing this path integral brings us back to this original form of the deformation. And of course, writing it in this way is suggestive, because this is exactly the way that a metric for our two-dimensional theory would couple to the energy momentum tensor. So a natural next guess would be that perhaps the correct way to think of these theories would be by taking our original quantum field theory and coupling it to gravity with some specific form of the gravitational theory. So of course, this is not exactly correct, because we know that the deformation is not exactly given in this form, because again, at higher orders in alpha, the energy momentum tensor also changes. But one can guess that perhaps there is some type of gravity theory for which this would be correct. Now, if you try to guess theories of that type, then again, you run into some immediate problems. And so first of all, there's one problem that you don't run into. If you would have tried to use this in higher dimensions, then you would immediately run into the problem that gravity is not renormalizable. So this doesn't make sense as a definition of a theory. However, in 2 dimensions, gravity is renormalizable. So it is sensible to try to define our theory as a quantum field theory coupled to gravity. So at least from that point of view, we are on safe ground in this case. However, there is another problem, which is how many degrees of freedom we get if we couple our field theory to gravity. So I remind you that a theory of gravity is a theory of the metric tensor, essentially, g mu nu. And if we're in d space-time dimensions, then this has d times d plus 1 over 2 independent components. Now, if we're looking at a theory of gravity, then we can ask how many physical degrees of freedom are in this graviton field. So a theory of gravity has to be invariant under diffeomorphisms, which take x to the coordinates x to any function of the coordinates. So this gives us d gauge transformations, which we can use if we want. So this gives us d different gauge transformations that we can use to gauge fix and get rid of some of these components of the metric. So in particular, we can, if you want to do some gauge fixing, that will get rid of d of these degrees of freedom that we have in the metric. And then after that gauge fixing, if we want to count the physical degrees of freedom that we remain with, we also have to impose the equations of motion of the components of the metric that we gauge fixed. So we get the additional constraints on the number of physical degrees of freedom in our theory. So if we have a theory of gravity in d space-time dimensions, then this simple counting tells us that it has 1/2 of d times d minus 3 degrees of freedom. And of course, you can check that if we're in 4 space-time dimensions, then this gives us exactly the 2 degrees of freedom that we have for the graviton in our universe. Now, unfortunately, if we try to do this now for the case of two space-time dimensions, then we find that the number of degrees of freedom in gravity is equal to -1. So what that means is that when you couple a two-dimensional theory to gravity, instead of adding to it extra degrees of freedom, as you may think, then you're actually subtracting a degree of freedom, in the sense that the space of physical states is smaller because of some extra constraint that you get on it. And of course, that's not what we wanted. What we want is to have some smooth deformation of the spectrum, say, given by these theories, where we don't reduce the number of states, we just deform them continuously as a function of this parameter. So in some sense, what we want is to couple to some theory that has 0 extra degrees of freedom, but that just modifies the spectrum somehow. While if we naively couple to gravity, then we would reduce the number of degrees of freedom by 1. So what we need is we need some type of theory of gravity that, so what we need is a theory of gravity that has 0 degrees of freedom, namely it has 1 extra degree of freedom compared to just the degree of freedom in the metric. And we also needed to have some dimensionful parameter that could be related to this deformation parameter alpha, which of course we have as part of our definition of the theory. I remind you that if we just have a theory of 2D gravity, then the Einstein term is dimensionless, and well, it's even topological, so that doesn't give us any dimensionful parameter. So we have to look elsewhere to find dimensionful parameters. So luckily, we encountered exactly such a theory of gravity just a few days ago, and also today in Douglas's talk. And that's the theory of Jakiv-Teitelbaum gravity. So we're going to guess that perhaps the correct way to describe these TT-bar deformed theories is by taking our matter theory and coupling it to this theory of Jakiv-Teitelbaum gravity. So the guess would be that maybe the correct action to use is the action of this Jakiv-Teitelbaum gravity coupled to our original matter theory. So in this theory, we have the fields of our original quantum field theory. Let me call them psi. We have the metric, g mu nu, and we have this extra scalar field phi, which I think for simplicity I'll denote with a small phi instead of a capital phi, but it's the same phi that was in Douglas's talk. So what is the theory? So first of all, we couple our matter theory to gravity just in the usual way by looking at the theory in curved space with this metric g mu nu. So that's the standard coupling to gravity. And then which Lagrangian do we use for the gravitational field? So we're going to use essentially the same Lagrangian that appeared in Douglas's talk. So in Douglas's talk, he had this Lagrangian of the scalar phi times the curvature plus 2. But we're going to do two small changes here. So the first change that we want to make is that Douglas wanted to describe a theory in an anti-de Sitter space, and indeed having this plus 2 here imposed that we had a space of constant negative curvature. But for the purposes of describing these TT-bar theories, then we don't, well, it will turn out that the correct thing to do is to look at flat space-times, which is natural because our original field theory, at least we know that it can live in flat space because that's where all the computations that we saw last week were performed. So we're going to drop this term. I mean, one can think of this term as actually, if you reinsert the ADS radius, then this term is really 2 over the ADS radius squared. So you could think of this as taking the radius of curvature of ADS to infinity. So that's one modification. Now, if you just do this, then we're left with a theory of flat spacetimes, but it doesn't have any dimensionful parameter. So the other thing we're going to do is we're going to introduce into this theory a cosmological constant lambda. And this is a very natural thing to do because, of course, in a theory of gravity, I mean, this is, if you want, the most relevant term that you can write down involving the gravitational field, and it will naturally be generated whenever you have a theory of gravity coupled to matter, then you will generate such a cosmological constant term. There's no natural way to avoid it. So this will be the theory that we'll talk about, and once we have this cosmological constant, then of course this has a scaling dimension 2, the scaling density of an energy density in 2 dimensions. So we have the option of identifying this parameter with the inverse of this parameter alpha that appear in the TT-bar deformed theories. Yes?
You have to include also the ghost part of the gravity, right?
Yeah, I haven't done any gauge fixing here. I mean, I'm writing here the action. This is a diffeomorphism invariant action. If I gauge fix, then of course I will have to deal with all the issues that you mentioned. But for now, I have not performed any gauge fixing.
But then there will be contribution to the energy momentum tensor also for the BC, right? So when you write the determinant of T, it's just a determinant of T of the letter?
So again, these are two independent descriptions. I mean, so we had the description here on directly from the field theory, where I do this deformation. But I'm now suggesting that the same theories have a completely different description, where instead of using the energy momentum tensor and so on, as I did there, I'm going to conjecture that the same theories can be described by just coupling our original theory to a metric and to a field phi with this action. I mean, so again, here the energy momentum tensor doesn't show up, and of course it shows up here in putting my theory in curved space, but that's implicit in this description. And this is the action that I'm going to take. And again, as usual, in the path integral, of course, I'm going to have, because it's the theory of gravity, I'm going to have to divide by diffeomorphisms as I described. So if I then gauge fix, I'm going to get some ghosts, as you mentioned. But the path integral is just now going to be the path integral over my original quantum field theory, over this G mu nu, and over phi divided by diffeomorphisms with an action, which is exactly this action that I wrote down here.
So where is alpha
Yeah,
here?
okay, so good. Where's alpha? So the conjecture is going to be that this theory is the same as the theory that I wrote down before, where lambda is -1/2 alpha. So again, this has a single parameter lambda. My original theories had a single parameter alpha. So if they're equivalent, then, I mean, by dimensional grounds, they'd better be related in this way. And the claim is that indeed this is the relation between these two theories. And I'll now try to present some of the evidence that this claim may be correct. So questions?
If you take the derivative with respect to alpha of this one, do you get determinant of T on the left?
Well, it's not. Again, this is described in a different language. I mean, it's not. I mean, here I'm writing it in a different space. Sorry.
This definition that you wrote over there and the derivative of that.
Yeah. Okay, but so I did not yet say. Okay, maybe you can ask that in a moment after I say exactly in what sense. I mean, so when I said that they're the same, then I still have to add some words of exactly in what sense they're the same, because well, I'll describe in a moment. Of course, a theory of gravity doesn't really live on a fixed space-time. In a theory of gravity, we integrate over all possible metrics. So if I want to say that a theory of gravity is equivalent to some field theory, then I have to say on which space does that field theory live. So before I say that, I cannot even try to answer your question of how to relate these two types of descriptions. Yes?
So if this equivalent is true, it already tells us that there is no hope of generalizing it to high dimensions, right? Because gravity is not unified.
Yeah, that's right. I mean, at least not in this formalism, then yes. In this formalism, indeed, it looks hopeless to generalize it to higher dimensions. Unless, well, I don't know, maybe you could imagine coupling it to some topological gravity in higher dimensions. I mean, so, okay, maybe it's, I mean, this theory of Jacobi-Teilborn gravity is in some sense topological. I mean, it doesn't have any local degrees of freedom, so you could imagine maybe coupling it to some type of topological gravity in higher dimensions. But okay, I don't think anybody has so far been able to make sense of that, but you can't rule it out completely. Yes?
So do you have higher orders simplified? Because otherwise it just gets
No. No. So this is the definition of the theory again, just like in the case that Douglas described. So this is just the definition of the theory, and again, you can just do the path integral over phi, just like in Douglas's talk, and replace it by a delta function of this curvature. So, the role of this phi is essentially just as a Lagrange multiplier. That I mean, of course, you can also integrate out other degrees of freedom if you want, and then you'll generate some action for phi and so on. But we're going to take our bare action at least to have this form. Yes.
Why are you not including the boundary term? Because
Oh yeah, sure. If I'm going to discuss cases with the boundary, then of course I should also include boundary terms. So yeah, so thank you. So in these talks, for simplicity, I'll only discuss the cases without boundary. I mean, so the cases that Sasha described in his talk. So we had this case of flat space where we do some S-matrix, and we had this case of a theory on a circle. And in those cases, we don't have a boundary. But indeed, I could also discuss the theory on an interval with some boundary conditions and so on. And then definitely, I'm going to have to add also boundary terms here. And there may also be some freedom there on exactly which boundary conditions I put into my field theory and so on. So then I have to add some more information. But for simplicity, I'm going to just discuss closed manifolds here. Okay, so that's an excellent question. So alpha to 0 means taking lambda to infinity. And OK, in this formula, that looks like a very ugly limit. But OK, we'll see. I hope it will become clearer exactly what you get in this limit. But yeah, that's a good question. But of course, for this equivalence to make sense, it had better be true that as lambda goes to infinity, we go back to our original quantum field theory. So essentially, this factor goes away, and g mu nu just goes over to eta mu nu, so that we get back our original theory in flat space. And that will be correct, but it will not be completely obvious in this formalism. Any further questions? OK, so in order to check that this is the correct theory, then we need to show that it has the same properties as the TT-bar deformed theories, for instance, the same energy spectrum, the same S matrix, and so on. But for that, we really have to say on which space does this TT-bar deformed theory live? Because here, we wrote this as an integral over some space, but of course, this is a diffeomorphism invariant theories. I mean, there's no preferred space. I could use the coordinate sigma or sigma prime and so on. This theory is completely diffeomorphism invariant. So the question is, which space does this TT-bar deformed theory look like? For instance, if I want to compute energy levels as a function of R, then of course I have to say what is that circle R that my theory lives on, because from the point of view of this theory, any circle is equivalent to any other circle by diffeomorphism invariance. So we'd like to have the coordinates that the TT-bar so we'd like to have some preferred coordinates in this theory that will be the coordinates of the space-time that the TT-bar deformed theory lives on. And the claim will be that these coordinates, in some sense, emerge dynamically out of the dynamical fields of this theory. So as we'll see, the coordinates are going to be essentially operators that are related to this field phi in the way that I'll describe. So the dynamics of this theory will construct for us a preferred set of coordinates, and those will be the coordinates that the TT-bar deformed theory will live on. So how does this work? So let me first consider the classical equations of motion of this theory. So there's one equation of motion which is obvious, which is the equation of motion of phi, which just sets r equal to 0, which in 2 dimensions means that also the Riemann tensor vanishes. So we just have a flat metrics, or metrics that are locally flat. And then we have the equation of motion of the graviton. So we have to consider the functional derivative of this action with respect to g mu nu. If we add the standard Einstein term, then we know that its functional derivative will give us r mu nu and r times g mu nu. And we get terms like that here. So if we take the functional derivative of this, we'll get terms that look like phi times r mu nu and phi times r. But we know that those terms are going to vanish anyway because we have the equation of motion that sets r to 0. So what else do we get? So we have some terms coming from here that involve also cases where we have derivatives of phi coming in from the equation of motion of g mu nu. And so if you compute the functional derivative of this term, of first this term with respect to g mu nu, then you find, if you do it carefully, you find minus the second derivative of phi plus 2 times g mu nu e squared phi. So this is just algebra. Then the second term is just the standard cosmological constant term. So taking the functional derivative of this gives us plus lambda times g mu nu, just as usual in Einstein's equations with a cosmological constant. And then in the matter part, then essentially by definition, taking the functional derivative with respect to g mu nu gives us t mu nu. So these are the classical equations of motion of this Joukiev-Teitelbaum gravity plus matter theory. And the first thing to ask is, what does the vacuum of this theory look like? So in the vacuum, we expect that t mu nu will just be 0. We're putting the quantum field theory in its ground state. Again, I'm doing this classically now, ignoring any Casimir energies or anything like that. And you can then show that there is a solution to these equations of motion. So since r is equal to 0, it's not surprising that there will be a solution which is just a flat space. So again, of course, we have many solutions because we have diffeomorphism invariance. Here I'm just writing down a specific solution. So there's a specific solution to these equations of motion. So g mu nu equals eta mu nu obviously solves the first equation of motion. But here in order to solve this equation, we see that we need to have some non-trivial derivatives of phi that will cancel this cosmological constant term, and it will be convenient to use, so here I was already using light cone coordinates, so I'm writing things here for convenience in terms of light cone coordinates, 1 over square root 2 sigma 0 plus minus sigma 1, or I guess here I'm going to be in Euclidean space for simplicity, because that's also where most of the computations were done, but okay, we can go from Euclidean to Lorentzian whenever we need to. So in these coordinates, the flat metric looks like this, and the equation of motion so if we plug in this metric, then the equation of motion for phi takes the form d plus d minus phi equals lambda, or 1/2 lambda more precisely. And so this, of course, is an easy equation to solve, and the general solution is that phi is equal to lambda over 2 times sigma plus sigma minus plus some constant plus times sigma plus, a constant times sigma minus, and a third constant. So this is just a general solution to this equation. So we see that this field phi is very far from a constant. So this is very different from the solutions that Douglas was describing in the context of AdS2. So here phi is linear in these coordinates sigma plus and sigma minus. In terms of the usual coordinates, it would go like sigma 0 squared minus sigma 1 squared if we're in Lorentzian space. Or and so it takes this form. And we have a freedom here of adding any linear terms in these sigmas. Of course, we can always get rid of those just by shifting our coordinates sigma if we want to. So this is what the vacuum looks like in this theory. And we see that in this vacuum, the coordinates are related to derivatives of this field phi. So we see that in the vacuum, we have a relation that tells us that sigma mu is essentially minus 2 over lambda times eta mu nu d nu of this scalar field phi. So at least in the vacuum, our coordinates look like just derivatives of this scalar field phi. And then the claim of, the content of this equivalence between Joukiev tidal ball and gravity and the TT-bar deformed theories will be that the TT-bar deformed theory lives on a space whose coordinates are given by x mu's, which are operators in this theory related to the derivatives of this scalar field phi. So schematically, we're just going to define these x mu's in this way. If we do it, we can be more careful about exactly how we do this when the metric is, when we're not in the vacuum, then, okay, we can be a bit more precise. So we're going to have here some factors. Well, okay, maybe I won't go into the details. If we're doing this in a general configuration, then this will be replaced by the Weizmann. So, of course, eta mu nu appears here because we're doing it in the vacuum. If we're going to do this away from the vacuum, then eta mu nu will be replaced here by the Weizmann of that, if you want the square root of the metric, but the details of that will not be important for us. So the claim is, again, that the way that this identification works is that we have this theory. In this theory, again, we have diffeomorphism invariant theory, but we have some preferred coordinates that are related to the scalar field phi in this way. And if we work in those coordinates, then we reproduce the TT-bar deformed theory. And of course, it's highly non-trivial from here to see, for instance, a relation to these formulas where we worked in our original coordinates and deformed by TT-bar, but it can be done. But that's not what I'll do here. Yes?
I'm just a little confused about how phi sets its coordinates, because phi is quadratic, and it's clear that it sets a 0 point from, say, the minimum of the quadratic.
Mm-hmm.
So
we have two coordinates. I mean, so each derivative gives me one coordinate. So this gives me two coordinates. Now, you're right that here you may think that these two coordinates are not independent of each other. So, but we'll see that actually, okay. So first of all, that's if you want, that's a feature of this theory that they're not completely independent of each other. But we'll see that at least on shell, if you look at the solutions to the classical equations of motion, then we'll see that they do behave like classical coordinates in the way that you would expect them to. But you're completely right that in general, these are now operators that don't commute with each other and so on. So that's, if you want, a feature of these theories. But for instance, okay, one test that you can make here, again, I'm not going to describe the details of this, But as was asked before, we expect that in the limit that lambda goes to infinity, this will go over to being a standard field theory. And you can check, for instance, if you compute the commutator of these coordinates, then you'll get a factor of 1 over lambda coming from here. And therefore, these commutators will go to 0 in the limit where you go back to, when you're expected to go back to a standard field theory. But again, in general, these XQs now are complicated coordinates, complicated operators in this language, but those are what you should think of as constructing the space-time of these TT-bar deformed theories. And so what I'll do, I'll present a specific computation to see how we can use these coordinates. So I'm going to compute the S matrix in these coordinates and show that we reproduce the formula for the S matrix in the TT-bar deformed theories that Sasha discussed last week. Yes?
In 2 dimensions, the general solution for R equals 0 is not just G mu nu equals eta mu nu, but there could in general be a conformal factor e to the 2 phi, where phi is some harmonic function.
That's right. So I was not saying that this is the most general solution, of course, but this is the solution that's going to be relevant for identification with the TT bar.
If we add that extra complication, will that change any of the qualitative features that you are going to discuss later?
Well, again, it's not a complication in the sense, I mean, it's already in here, right? I mean, we were saying that the full path integral of this theory is equal to the TT bar deformed theory, so of course that includes all of these configurations that you were discussing. I mean, I was using this specific solution just to motivate why it's natural to think of the coordinates as related to derivatives of this phi, and that will also be true for all these other solutions. But again, the precise relation, the precise description of them in terms of these coordinates sigma will be different if you take a different metric here. But this relation, or its more precise generalization that I'm not writing down here, that involves the metric, is a precise definition of the coordinates of the field theory, and that is diffeomorphism invariant if you write it in the right way, and valid in any configuration. Yes?
I'm trying to think of this using string theory, and the fields x mu look like both target space coordinates and the worldsheet coordinates. Should I not be thinking this way?
Okay, that's a very interesting question. But yeah, in some sense, you should be thinking about it this way. So it's not evident from the way that I wrote the theory here, but it's true that these x mu's are dynamical fields in this gravitational theory. So they're dynamical fields coupled to gravity. So it looks like you had these x's and you had the original theory and you coupled it to gravity. So in that sense, it looks very much like a string theory propagating in the space of g mu nu and x. And so that's something that I was going to say at the end, but maybe I'll say it now. So this will relate to the previous discussion that maybe this thing should be thought of as a sector of a free string theory in some sense. So you can rewrite this action. You can do some change of variables, which I hope I'll have time to describe, but that rewrites this action in terms of the x's instead of in terms of phi. And then it really looks like some string theory whose target space involves your original matter CFT or whatever it was, plus these extra coordinates x. But the point is that now, because we want to think of these x's as the coordinates of our field theory, then we're going to look at configurations where the string is stretched along these x coordinates. So if you want to think of that language of string theory, then if you want to have you're looking at the configuration where you have a very long string that fills that fills x0, x1 if you want. And so you can think of the theory as being some sector of a free string theory where we have a string that just fills all of these two directions, and it's some configuration in the other directions. So that's definitely one way to think about this theory. Of course, it's free because we didn't put in any interactions between the strings. So this is definitely one way to think about this theory. And again, and the relation between these x's and, say, the sigmas is the usual relation between worldsheet and space-time coordinates in string theory that you would have. Again, now just in classical string theory for a single string worldsheet, which is all that we have in this context. I mean, so we're not going to second quantize these strings or anything. I mean, this is just the theory of a single string in that language where we have a single long string. But that is one way to get intuition for why this will indeed give us a Hagedorn spectrum, because in that sense it's very closely related to the standard string theory. More questions? Okay, so let's see how we compute using these variables. So what I'm going to compute is, let's see, I'll write it here. So what we want to do is we're going to compute the S matrix of this theory. Now, of course, at first sight, this looks very complicated because we have here this original theory coupled to gravity with these extra degrees of freedom. But we'll show that indeed the S matrix of this has the correct relation to the S matrix of the original theory before we coupled it to gravity. So we're going to discuss now some configuration, as usual in the S matrix, where we have some particles coming in, which are very far separated from each other in the infinite past. Then they interact, and then we have some number of particles coming out in the far future. And the assumption, as usual in the S matrix, is that except for these particles, in the past we're just in the vacuum. So in between these particles, we have here the vacuum, also here the vacuum, and so on, in all the regions between these particles. And then here we have some wave packet that's coming in, corresponding to some particle state. Now, in each of these vacuum regions, then we're just going to sit in one of these vacua. So the field X will essentially be just the same as the coordinate sigma. Well, we can just treat everything classically. But when we pass through this particle, then this particle will carry some energy momentum. It will be a source for this field phi, and it will then give us a non-trivial relation between these operators X, which are the coordinates of our TT-bar deformed theory, and the coordinates sigma that appear here in the action, and that is what will give us the S matrix. So that's the plan. So how do we do the computation? So to do the computation, it will be convenient to fix a gauge for the gravitational action. And we're going to work, as is standard in string theory. So we're going to fix to conformal gauge. So our action is invariant under diffeomorphisms. So we have two diffeomorphisms. We can use them to fix two of the components of the metric to any value that we want. And it will be convenient to fix them such that the metric is proportional to the identity matrix. Namely, it's equal to e to the 2 omega times eta mu nu for some scalar function omega. So this gets rid of all the components of the metric that are not proportional to the identity matrix. And this completely uses up the gauge freedom that we have in this action. And so so if I do this gauge fixing, what do the equations of motion look like in this gauge? So first of all, we have the equation r equals 0. So in this gauge, this becomes the equation d plus d minus omega equals 0 that just I mentioned before. So we want to, so we have this equation of motion, and then we have the equation of motion of the metric, which just plugging in this configuration, they take the following form. So we have the equations. We have the equations of the off-diagonal, if you want, components of the metric, which are now constraints coming from this gauge fixing, and they take this form. And then the more interesting equation involves d plus d minus phi, which was non-zero already in the vacuum configuration, and that's in this gauge it's equal to 1/2 lambda e to the 2 omega plus t plus minus. So these are the equations of motion that we have to solve. And we're going to solve them in the context of configurations like the ones that are hiding behind here, where we have the vacuum almost everywhere, but perhaps with some particles carrying energy and momentum in between. So the fact that we have the vacuum far away, so in particular, we're going to have a flat metric far away. So that tells us that the only possible harmonic function here is just 0 up to a shift by constant or something that's irrelevant. So, well, if it's just fixed boundary conditions such that eta mu nu is equal to, well, g mu nu is equal to the identity far away from all the particles, then that uniquely fixes omega to be equal to 0. And then I want to rewrite this in the language of these new variables x mu. So if I rewrite these equations of motion in the language of the x variables, let's see where I can do that. So let me do that here. So we want to solve for how these x variables are related to the sigma coordinates of the worldsheet. So now, when I went to the conformal gauge, I do have some fixed coordinates sigma, which are the coordinates in this conformal gauge. But again, they're not going to be the same as the coordinates that the TT-bar deformed theory lives on. Those are given by this expression. And the coordinates of the TT-bar deformed theory obey a relation. So if we plug in the relation that we had before, then we find that d plus of x minus is minus 1 over lambda times t plus plus. D minus of x plus is equal to minus 1 over lambda t minus minus. and d plus of x plus is equal to d minus of x minus is equal to 1 plus 1 over lambda times t plus minus. So here I just rewrote these equations of motion using these new variables x mu that I introduced before. So there are two things that you can see from here. First of all, you can immediately see that if I don't have any energy momentum, then x plus is just the same as sigma plus up to a constant shift, just like we saw before in the vacuum. So d plus x plus is independent of x minus, and it's linear in sigma of sigma minus, sorry, and it's linear in sigma plus. And the other thing we can see is that some of you were rightly suspicious that if I define two coordinates in terms of a single field phi, then they would not be independent of each other. But here we see that at least classically, I do land on my feet because, let's see, where did the yellow chalk disappear? So we should verify that if I take d plus of this equation, which is one constraint that I have on d minus, on d plus, then it should be the same as d minus of this equation. Otherwise, these equations do not consistently define any classical solutions for x plus. But luckily, that's the case because d plus of this vanishes, of course, and then the fact that the energy momentum tensor of my original conformal field theory, or my quantum field theory, is conserved, tells us that d plus of t minus minus is exactly the same as d minus of t plus minus. So in that sense, at least classically, we can always solve these equations and get some well-defined solution for the x's. So what do those solutions look like? So yeah, should I erase this now? So what are the solutions to this equation going to look like if I now have some scattering state of particles here? So so we can start by looking at the vacuum state. So if I have the vacuum state, then that's just well described by this classical solution where the expectation value of x plus is equal to sigma plus and the expectation value of x minus is equal to sigma minus. But now let's consider, instead of that, some single particle state, say, where we have some particle moving in the vacuum. And again, I'm going to, even though already if you're in momentum space, then we're going to assume that this particle is really some wave packet, which is localized, such that I have a vacuum on both sides of it, but I have some energy moving along with that particle. So in a configuration like this, then again, on both sides of the particle, x is going to be linear in sigma, but I can integrate. So I can integrate these equations, just classically thinking of them as first-order equations for phi, for x, and we see that if I cross some particle, then I get some contribution from the integral of these t's over the wave packet of the particle, which will just give me the energy and momentum of that particle. So if I just solve these equations of motion in the presence of a particle, then so I can just take the. So let's think of it by taking the expectation values on two sides. So we see that the expectation value of x will jump by some integral of the expectation value of t, which is just the energy of my particles. So for instance, in a configuration of this type, if this particle carries some momentum p plus p minus in light cone coordinates, then on one side of that particle, I'm going to have that x is shifted is shifted by, say, minus p plus of the particle over 2 lambda. And on the other side, x plus is going to be sigma plus p plus over 2 lambda. So as I cross this particle, my dynamical coordinate x plus jumped by p plus over lambda. So that's, again, easily seen from these equations of motion hiding behind this blackboard when I integrate them across the path of a particle. And similarly, if I look at x minus, then its expectation value will jump by an amount that's proportional to p minus over lambda. And again, for this, of course, I don't need to know anything about the configuration of the particle, only the fact that it carries some energy and momentum. So this gives us an example for how when we go away from the vacuum, these x's are no longer exactly the same as the naive coordinates sigma in this conformal gauge, but rather they're shifted from them in a way that depends on my on the precise state that I'm in this case, for a one-particle state. Any questions about this? Okay, so now let's try to compute what the S matrix looks like in this deformed theory using this approach. So first of all, one important thing is that this equation tells me that G mu nu is just equal to eta mu nu here, which means that in this gauge, then the matter essentially is completely decoupled from these coordinates x. So the matter action is just action in flat space if I work in the original sigma coordinates. I mean, so this of course is true in my original sigma coordinates. So the matter action is completely decoupled from whatever happens with this phi field, and therefore with my coordinates. And what that means is that the S matrix. So the S matrix in the sigma coordinates equals, if you want, my original S matrix before I coupled the theory to gravity. So it looks like everything is trivial, but the non-trivial part of the S matrix will come exactly because I now want to work with these deformed coordinates x instead of the original coordinates sigma of the conformal gauge. And that will give me a phase shift when I go from the original sigma coordinates to this x coordinate. So what we want to say is that the correct, say, single particle state, so some in state, instead of being some integral, say, schematically of a dagger times e to the I p mu sigma mu, is now going to be, in the deformed theory, it's going to behave like, so again, this is an integral, dp, or well, d2p. So, well, okay, for particles, I guess we have here a single momentum, and the energy is determined by the momentum. Then then in the deformed theory, I'm going to demand that we have the same expression, but where here we have these dynamical coordinates x mu. So what is the effect of doing this? So suppose that I now look for simplicity, say it's some two-particle state. So I want to discuss, say, a two-particle state of this form. So this will be my my in state, say, and then we're going to take it to the out state. So how does this in state now differ from the in state that we had in our original theory? So if I just act with this a dagger p1, or well, okay, I really want to act with this wave packet. So if I act with this on the vacuum, then in the vacuum x just takes its trivial value, so this is going to be the same as this. However, if I then take my second particle, so I'm now going to put in, so I'm assuming now that I have the state of the first particle, and now I'm putting in another particle here. So I'm going to put here, so this particle now has p1 plus p plus minus, p1 minus, and I'm going to put here now another particle, and I'm going to assume that the velocity of this particle is slower, or is smaller than the velocity of my original particle in the positive direction, such that at very early times this particle is to the left, and this particle is to the right. So if I do that, then if I now act, so when I act with so when I have here this e to the I p2 mu x mu, then that's going to be e to the I p2 plus times x plus, but where x plus now acting, I should probably write it with lower coordinates. So x plus now is going to act on this one particle state, and it's going to give me this, it's going to include this shift by minus p1 plus over 2 lambda plus sigma plus, and a similar expression coming from p2 minus, so there's going to be a term p2 minus times p1 minus, p1 minus with that. So I'm writing it here with one upper and one lower indexes. Index, of course, they're raised and lowered with this matrix eta mu nu. So so this in state in this now in these new x coordinates, if you want, is going to be the same as the in state in my original sigma coordinates times this phase that I get by doing this change of variables. And this phase is exactly the same phase that we saw in the S matrix of the TT bar deformed theory. Namely, it has a sum over all pairs of particles. Here I did it just for one pair of particles, but it's hopefully obviously the same for any other pair of particles of epsilon mu nu, pi mu, pj nu, where again the ordering here is determined by the ordering of the velocities of these particles, which is the same as the ordering of their positions in my initial state. So in this way, going to these new dynamical variables gives me this extra phase in my definition of the initial state. And now we're basically done, because we know that the S matrix in these coordinates is exactly, in the sigma coordinates, is exactly the same as it was. So what I find is that this new S matrix in the theory with parameter lambda is related to the original S matrix for lambda equals 0 times these phase factors coming from the initial state, and I'm going to have exactly a similar phase factor coming also from the final state. So I'm going to get expressions that have, so again, this sigma pi with pj from the initial momenta, and a similar phase coming from the final momenta. And then by matching these phases with the phases that we saw in Sasha's talk, we can see that they're the same if we have this relation between the cosmological constant here and minus 1 over 2 alpha here. So essentially, if you want, this is almost a proof that this theory is the same as the other theory, if we're assuming that once you know the S matrix, then that uniquely defines a theory, at least for some purposes. Then this is essentially almost a proof that this deformation indeed reproduces the alpha deformed TT star theories with the specific identification of the parameters and with the specific identification of the coordinates that, well, that's hidden somewhere behind these blackboards. So any questions about this? Yes? Well, it's yeah, so I was sort of not being precise about which parts are classical and which parts are quantum, but the idea is that you should really think of it as working with expectation values, but it's justified in these configurations that we're in. I mean, so say this, so the equation of motion, we could think of it as an operator equation for this x, and then t, and then the integral of the expectation value of t over this particle is just the total energy and so on of that particle. So for the purposes of this computation, it didn't really matter if I was doing it classically or quantum mechanically, if you want. I mean, so there are going to be some strong quantum interactions maybe inside this particle, but all that I was using for this configuration is how the parameters are related far away from the particles, and for that, this classical analysis is enough. Well, it's essentially exact. Yeah, I mean, so again, the loops are maybe important for telling me precisely what's the configuration of these particles and so on, but they're not important for. So yeah, so the claim is that this is exact in this parameter lambda, with no, without needing any extra
So how do you say that
limits.
this
Yes.
coupling to the objective factor bound gravity is equivalent to this bar?
Oh, if you want, that's how I see it. I get the same S matrix from here and from there, so it's the same.
That was the result for the bar, you say, and now we get
Yes, now I get the same result from these theories in a completely different way and a completely different language, but that's what I get.
Yeah, I don't know. It's a stupid question. I mean, because it's theory of gravity of a sort. I mean, defining S matrix is not as unique as you have in flat space. So technically, here you have the Lagrangian plus instruction to read asymptotic particles in the coordinates defined by this x.
Exactly.
Right. But that's sort of technical definition of this matrix. Do you have some idea how to define this matrix in terms of the field configuration phi? What has to go to zero in the future?
Yeah. So again, so I wrote down the vacuum. I mean, so the assumption is that far away from all the particles, I just have the vacuum. I mean, so I really
I
go.
don't know anything about particles.
Yeah.
I see this field, and
Mhm.
you tell me that the symptotic domain is where the metric is
This is flat.
already.
That's right.
But something has to happen with the field phi.
Mm-hmm. Right.
When you go to asymptotic domain.
Yes.
There, maybe it's obvious, but not obvious to me.
Okay.
What to demand of the field phi
So if I demand that symmetric is flat, then that tells me that this phi is this given by this minus lambda over 2 sigma plus sigma minus. Say that I work in conformal gauge. I mean, you'll allow me to work in gauge.
This is vacuum solution.
Exactly. So in the vacuum, we have this behavior, but with some shift. And my boundary conditions are going to be that I'm going to demand that phi takes this form up to some shift, which will depend on the precise state of the theory.
If you go to a symptotic domain of large time,
Well, this is for large space, I meant for...
large space, large time. But what I'm saying is that that's the vacuum solution.
Mhm.
But you assume that there are some particles flowing.
That's right.
So it's modified by the, because that's vacuum solution.
No, this is the vacuum. Well, but far away, I want to have the vacuum far away from all the particles. And so the idea is that far away from all the particles, I have this, and in particular, in asymptotic space on both sides, I have this.
Well,
Then the particles, of course, you can ask how I define the particle states. Of course, that's complicated as
I
usual.
don't see how it
but-
defines the notion of a matrix uniquely.
Mhm.
It probably does, but it's not obvious.
Okay. Well, okay, maybe we can discuss it later. Let me just mention to end this part of the talk that, of course, there's also another way that I could have done things. So we're saying that these x's in this language are now these complicated operators that I have to follow in order to translate between this theory and the TT-bar deformed theory. Of course, there's naively a simpler thing that I could do, which is just to work in directly fix my coordinates instead of going to this conformal gauge. I could have also just fixed my coordinates to exactly be these operators x mu, which are related to these derivatives of phi. So that would correspond to directly working, if you want, in the physical coordinates of the TT-bar deformed theory. So I can do that also. The disadvantage of doing that is that then the action becomes complicated and interacting, and I wouldn't know how to compute the S matrix directly. But for the purposes of these questions like defining the S matrix and particles and so on, I think it may be easier to go. So this is what's often called the static gauge in this language. So it's probably easier to go to this gauge. In this gauge, it's easy to say what I mean by the particles and so on. And then, but for the computation, it's easier to do the computation in this other gauge. But of course, if I did everything correctly, I'm going to get the same answer. So, I mean,
You showed that the two theories are equivalent.
yes.
What sense
Well, again, what I meant by the UV completion is just an explicit action that I write with this parameter alpha appearing in it. That's what I mean by UV completion. I mean a direct definition of the theory for every value of alpha, which is a normalizable field theory where I know how to do computations. Well, the previous one was not explicit. I didn't have an action as a function. Here I can, in principle, ask. So again, I won't have time to discuss these questions, and I don't know the answers to any of these questions that I wrote down in the beginning. But in principle, now that I have this action, I can answer all these questions of what are the operators, what are all the possible solutions of this theory, and so on. So now they become explicit.
You didn't yet tell us how TT-bar is.
Well, I told you in the sense that, I mean, I said that with this relation, and in these coordinates, you get TT-bar. Yeah, that's right. Yeah, so if you want, the claim is that, right, so the claim is that if I work in this gauge, the action is exactly the TT-bar deformed theory. Unfortunately, there it's harder to see directly because I get a complicated action and so on. I can see that in a classical limit and so on, perturbatively in this parameter alpha, I can see that I get the correct thing.
You didn't display this calculation.
I didn't display it, that's right, just because it's complicated. But I'm arguing, and again, it's in these papers that I wrote down. You can show that, but it's complicated, and again, that it's of course an interacting theory and so on. So in that language, it's going to be hard to do computations. But if you want, the claim is that is the TT-bar theory. But again, and working in a specific, in that specific gauge, the theory looks like it's not normalizable and so on. It's going to be maybe difficult to do computations, as you know, some gauges are more useful than others. So in this gauge, the theory looks complicated, but it is the same as the TT-bar deformed theory. Well, in this gauge, the theory is explicitly normalizable, and I can do computation in these other gauges, but there it's not obvious that it's the same as the TT-bar deformed theory. That's the claim. Oh yeah, well, you could go to any gauge you want, sure. But again, it depends which step. But first, we're interested in the solution. So for the S matrix, we're interested in solutions that take this form. So let me just yes.
Let me see if I understand. You have two theories. One of them is completely well defined,
Yes,
and the other is indirectly well defined.
that's right.
And you claim that the S matrix is the same,
Mm-hmm.
and the theory on the right does not have any Green's functions. Do you know about it?
Well, okay, it does in this fixed gauge, but yes, it does not have any naturally defined Green's functions. That's right.
The theory on the left does have naturally defined Green's functions.
Right, which you identify with the Green's functions in this gauge in this theory.
So
So they are by construction the same. But are they meaningful or not?
Yeah, normally
That's
they-
the open question.
Well, if the theories are equivalent, then they should be meaningful and natural.
Okay,
But
good.
they're obviously not.
Indeed. So those are open questions that I don't have anything smart to say about,
We
I'm
were
afraid.
instructed that in the theory of gravity, there is no meaningful.
Okay, good. But this theory sort of comes with this extra baggage of these preferred coordinates. So then I don't know. I don't know the answer to your question of are these good observables or not. Again, in this language they're very natural. In this language they're very unnatural. You can certainly compute them and ask what values they have, but are they interesting for understanding the short distance or high energy features of this theory? That I don't have anything smart to say about. Okay, so I'm now going to switch gears completely to holography, unless there are urgent questions about this topic. I'll also be in the tutorial this evening, so if there are non-urgent questions, then we can postpone them to the tutorial.
Spectrum of the circling?
Yeah, right. Okay, very good. So that's, don't have time to display the computation, but indeed you can, so computing the spectrum on the circle is more difficult, but again, you can essentially, well, what you can compute is the partition function of this theory on a torus. So you can put this theory on a torus and look at configurations where these x's sit on a specific torus if you wanted space-time of the string, and then compute the partition function and show that it's the same as the partition function of the TT-bar deformed theory, and therefore also the energy levels are the same. But that's a much more complicated computation. I'm not showing it here, but it was done up to various
Yeah,
caveats.
but there must be a subtlety which you probably didn't display because in order for this to work on a cylinder, on a torus, for instance, you cannot take phi, I mean, in the original formulation, you cannot
That's right.
take phi as a function, right? You have
No, I can take it as a function, but with specific boundary conditions that my worldsheet, if you want, these sigmas live on a torus, and as I go around this cycle of the torus in sigma space, x goes around some cycle of the torus that the TT-bar deformed theory lives on, and vice versa. So I'm doing the path integral of this theory with those boundary
But then
conditions.
you have to say that phi, when you
Yeah.
bring phi around that cycle,
That's right. Phi itself is not periodic, but x is periodic with the right periodicity and so on. So yeah, I have to put in these very specific
then
boundary
it's-
conditions,
it-
which are not natural from this Jakiv tidal volume.
built into operator formula is not necessarily.
Okay, but again, I mean, the point is just that you can write it down also in this language. It may not be natural from
So
the
in
Jakiv
fact,
tidal.
producing this action is not complete. I mean, you have to
Yeah.
supplement it with
Right, just like here I had to supplement it with which coordinates I'm going to use for the translation. So to do the translation to the TT-bar deformed theory, I have to say exactly what are these x's, what types of phis, what are the boundary conditions for these phis, which is the same as what are the configurations of these x's, and so on. So that's right. So there's definitely lots of extra adjectives that comes in here, but the claim is that it is well-defined, and you can write this as some specific path integral in this theory. Okay, so let me now switch gears completely and ask how these TT-bar deformed theories are described holographically. So as we already heard throughout this school, holography is a very useful tool, both for studying field theories and for studying quantum gravity. And so we'd like to know if holography can teach us anything about these TT-bar deformed theories or vice versa. Now, holography is useful in the context where the theory in the bulk is weakly coupled. So, well, for simplicity, when I discuss holography, I'll discuss the case where I start from some two-dimensional conformal field theory, which is dual to some quantum gravity theory on AdS3 space. It could be, for instance, string theory on AdS3 cross S3 cross D4. And so this is holography. And then I'm going to do the TT-bar deformation of this theory and ask what does that correspond to in this quantum gravity dual of that theory. And it's useful to work in the limit where the bulk is weakly coupled, and we can essentially do a classical physics in the bulk. And that's true if the central charge of my conformal field theory, which one can show is the same as the AdS radius in units of Newton's constant in the bulk, has to be much bigger than 1, or in other words, the curvature has to be much smaller than the Planck scale. So in that limit, the theory in the bulk is weakly coupled, and we can hope to find a useful solution of it just in terms of classical variables in the bulk. So how does the holographic dictionary work here? So we heard lots of different holographic dictionaries during this school, but I think we haven't seen yet, as far as I recall, at least the most naive holographic dictionary for how to map fields in the bulk to operators in the conformal field theory. So the idea is that in general AdS-CFT correspondence, the conformal field theory in its vacuum maps to just empty AdS3 space. And I'll write down the metric of AdS3 in these coordinates. So I'm going to, for the purposes of this part of the talk, I'll just describe the field theory in flat space. So we're going to get this Poincare patch of AdS3. And so I'm writing here AdS3 in these coordinates where the boundary is at z goes to infinity. So this is the vacuum of the field theory. And then if we want to look at general configurations of this quantum field theory, then they're going to be described by metrics that take the following form. So in any classical solution, at least, I can take the metric in this z coordinate just to be dz squared over z squared, and I can take the off-diagonal components to vanish. And then the metric in the other coordinates, in general, takes the following form. So this is what's usually called the asymptotically anti-de Sitter space. So we can have here some general g mu nu of x appearing, which in the vacuum, this is just eta mu nu. But we can have here also some more general g mu nu when we describe the conformal field theory in curved space. And then if we look at the most general solutions to the equations of motion, then we have corrections to this, which start at order 1 over z squared with a term that I'll call h mu nu squared. And then there are higher order powers of 1 over z. So this is what's called an asymptotically AdS solution. And what's the interpretation of these configurations in the field theory? So g mu nu is interpreted as the metric of the space that the field theory lives on. So a configuration like this describes the CFT on a space with the metric g mu nu. Of course, we can take it to be flat space if we're interested in the conformal field theory in flat space, but here I generalized it because it will be useful in a few minutes to a case where the conformal field theory lives in a curved space. And then the rest of so this mode is non-fluctuating, so it's reasonable to think of it as a parameter of the theory. In this case, the metric that the conformal field theory lives on. These other modes are fluctuating, and the interpretation of this first subleading correction h mu nu can be seen by computing the expectation value of the energy momentum tensor in these configurations. So one can compute just from gravity the expectation value of the energy momentum tensor once we know how to couple the field theory to a generic metric. So the expectation value of the energy momentum tensor is just the derivative of the action with respect to the metric. And so if you take a solution like this and use the equations of motion in the bulk, then you find that the expectation value of the energy momentum tensor is given by 1 over 8 pi g Newton times the AdS radius. I guess in some of these formulas, I set the AdS radius to 1, I guess, so there should be a factor of the AdS radius sitting outside here. So sorry about that. But the important point is that this h mu nu can be identified essentially with the expectation value of the energy momentum tensor in the field theory. So the usual rules of AdS-CFT tell me that if I want to describe the conformal field theory with symmetric g mu nu, then it will be described in the bulk by a metric of this type. And different states of the conformal field theory are going to have different values for this h mu nu, which will be related to the expectation value of t mu nu in these states. So that was just a very quick review of the original dictionary between the bulk and the quantum field theory in AdS-CFT. And now what we want to do is we want to add here a deformation of this TT bar deformation, and we want to ask how we add this to this boundary. So one thing we can do is we can take our Lagrangian and add to it some delta g mu nu of x t mu nu. So that's the standard type of deformation that we would add to a quantum field theory. And this deformation, of course, just corresponds to changing the metric. So we know that this deformation, we implement it by changing this boundary condition. So this, on the field theory side, corresponds to taking g mu nu to g mu nu plus delta g mu nu. Sorry for the upper and lower indices. But that's not what we want to do in our case. In our case, say at leading order, what we want to do is we want to take L and add to it something that's going to be, say, some constant times the integral of t plus plus x t minus minus x. So instead of adding here a constant, we have here a product of two energy momentum tensors. So what does this look like? In the large limit, these or in the large central charge limit in this case, these correlation functions essentially factorize. So we can think of this product of operators. So schematically, we can think of this just as adding a deformation of the metric that's proportional. So I'm being schematic now, but it can be justified by more precise computations. So schematically, what we want to do here is to take the metric in the G minus minus components and deform it by the expectation value of t plus plus. So that's something that would be equivalent to doing this. So at least if I'm in some classical state where we could just think of those as classical operators, then doing this deformation is the same as changing the metric locally by the expectation value of t plus plus again. All this is just at leading order in alpha. And I'm using it to motivate the claim that the correct way to describe a deformation of this type in gravity at leading order in the deformation is to change the boundary conditions such that, so previously, so for alpha equals 0, we had the boundary conditions that g mu nu is fixed and that h mu nu can be anything. But now that I do this deformation, or so say, let's discuss the field theory in flat space because that's the context where we're doing this TD bar deformation. So for alpha equals 0, we want g mu nu to be exactly equal to eta mu nu and h mu nu to be anything. It can take different values in different states of the theory. But now, based on these hand-waving arguments, we want to change the boundary conditions such that g mu nu, instead of being eta mu nu, it's shifted by alpha times this expectation value, which is the same as alpha times this second or subleading mode of the metric. So instead of taking the boundary conditions to be g mu nu equals eta mu nu, we now want to take them to be, if you follow correctly all the factors, minus eta mu nu minus c over 12 pi alpha times h mu nu. So I describe this here in a hand-waving way, but it can be rigorously shown that in the large central charge limit, the way to implement a deformation of this type, which is often called a double trace deformation for various reasons that I won't go into, is by changing the boundary condition for the graviton to take this form. So the idea is now that instead of, if we want to describe this deformation, instead of summing over all metrics with the boundary condition, with this boundary condition, we're now summing over all metrics with this modified boundary condition. So that follows from the standard rules of the ADS CFT correspondence. You'll note that what appears here is alpha times c. So it's important when I'm in this large C limit that I'd better scale this deformation parameter alpha like 1 over c if we want to have a well-defined limit. And that's not surprising because we also saw before that in the density of states also we had this combination of minus c times alpha appearing. So obviously if I want to have a well-defined theory, I'd better take this scaling that alpha goes like 1 over c. So for that scaling, the claim is that I get that the leading order in alpha effect of this deformation is to change the boundary condition in this way. So now this modification, the vacuum of the theory after this modification is still described just by empty ADS space because empty ADS space has h mu nu equals 0, so it obeys this boundary condition. But in general, the form of the fluctuations around this ADS space and also of excited states like black holes will now be different because they'll need to obey now this modified boundary condition instead of the original one. So, questions? Yes?
Can you do a similar process also for a deformation in higher dimensions?
Yeah, this is completely general for any double trace deformation. So any deformation that involves a product of two operators that are each dual to a particle in the bulk corresponds at leading order to this type of modification of the boundary condition. Now, of course, here I'm working in the classical limit in the bulk, and in that limit, this is well defined. If I try to go to higher orders, then I'll run into trouble because we know that this deformation is irrelevant, so its effects are going to grow larger and larger at high energies, which in this ADS context corresponds to going closer to the boundary. So if I would try to just do this and then compute quantum corrections, then I would find that they eventually blow up near the boundary, so this is not really well defined. But at least at leading order in alpha and at leading order in this 1 over c expansion, this is a valid rule for performing computations in these theories. Now the problem is that the deformation that I actually want to do is not this deformation, but it's this TT bar deformation where I don't just add this term, but I then continue turning on extra deformations such that I have, instead of this, well, okay, I won't write it again, but I want to turn on, for every value of alpha, I want the deformation to involve the energy momentum tensor at that value of alpha. So if I expand it in powers of alpha, it corresponds to adding more and more complicated operators here. And that we don't really know how to describe well in this gravity language. So the usual rules of ADS CFT don't tell me what I should do to describe the complete TD bar deformation for a finite parameter alpha on the gravity side. But there is a very interesting conjecture by McGow, Mazet, and Verlinde in this paper that I mentioned at the beginning, which is that the correct description of these TT bar deformed theories for finite alpha are not to change the boundary condition at z equals infinity, as we would do in standard holography, but instead to cut off space at some critical value of z, and then impose as a boundary condition that the metric at that specific value of z, so the boundary condition is that at z equals zc, the metric will take this form, so plus zc squared dx mu eta mu nu. So of course, ADS space, if I cut it off, it obeys this boundary condition. But in general, their claim is that you can replace ADS space by this cutoff ADS space, and this would describe the full TT bar deformed theory. Now I have to tell you how this parameter ZC is related to alpha. So that we can see just by matching the two computations already at leading order in alpha. So we can try to see when at leading order in alpha, when do these solutions reproduce this. So I can just plug in here. So if I compute this, so if I evaluate this at ZC squared, then I find that with the new boundary condition, we have here eta mu nu minus C alpha over 12 pi h mu nu plus 1 over ZC squared h mu nu plus dot dot dot. So I just plugging in the deformed boundary condition that I get by the usual rules at leading order in alpha, and evaluating those metrics at z equals zc. And we see that these things agree with each other if we identify zc with 12 pi over c times alpha. So at leading order, this has to be correct for the leading order deformation to match. And now we see that, well, the claim is that this is correct to all orders, of course, on dimensional grounds. There basically has to be some relation of that type. So this is, of course, a very interesting conjecture if it's correct, because generally in holography, we don't know how to define quantum gravity theories on finite spaces.
Do you want to emphasize that this makes sense for the sign of alpha?
Yeah, I'll say that in a moment. Right. But, so okay, maybe I'll say that now. So indeed, we see that this makes sense only when alpha is bigger than 0. So when alpha is bigger than 0, these boundary conditions that I get can be replaced at leading order by a boundary condition at some finite position inside the bulk. Well, if alpha is negative, then obviously we cannot do that. So if anything, then this describes only these theories that have alpha bigger than 0, which are problematic for various reasons that I mentioned. But still, even in that context, it would be very interesting if we can indeed describe holographically some finite region of space, which up to now holography is usually defined by going to the boundary and finding out what are the correct deformations of my boundary conditions and using them to construct a holographic theory. And this would be much more remarkable. Now, there's an interesting feature of this deformation that's related to the fact that it only works for alpha bigger than 0. So we saw that when alpha is bigger than 0, then the spectrum becomes complex. So we have a real spectrum at energies that are smaller than some parameter r over 2 alpha. But above that energy range, we get complex energies, and the theory is non-unitary. So what MMV suggests to do is just to throw away all other states that don't obey this. And that's motivated by the fact that if we do consider gravity in this cutoff AdS space, then there is a bound on the amount of possible energy that we can put in, which is the energy of a black hole that fills all of the space so that its horizon goes all the way up to ZC. And one can compute the energy of that black hole and see that it is exactly equal to this value. So the prescription of MMV is to just throw away all the other states and assume that the states that remain are an exact description of quantum gravity in this cutoff AdS space with this boundary condition. And so they make various tests of this wild conjecture. Many of their tests are just at leading order in alpha, so in that sense they don't really test, all they test is this standard rule of how we put in the leading order deformation into AdS space. Their main test, which is highly non-trivial, is that so they now look at black hole solutions with these modified boundary conditions, and they show that the energies of those black holes are now exactly given by this formula that we saw last week. That the energy is given by. So if we start from some black hole solution that originally had some energy E0, then the energy that you could compute just by solving gravity in the bulk with these modified boundary conditions at z equals zc reproduces exactly this energy formula of the TT-bar deformed theories. So this is a very interesting claim, and I'd be very happy if it's true and if I would be able to understand it. But there are many confusions that I have about this claim, so let me just finish by throwing away lots of confusions. But before that, maybe are there any questions about what the claim is? No, here it's plus. Again, here alpha is positive, and this is a +1. It's not the same as the other coordinate that you're used to. So I hope that I was being precise here. Yes. Yeah. So this is the sign that from the field theory point of view, I would say that it doesn't make sense, but okay, but one can still consider it, and in particular, if you throw away all the states that have complex energies, then by construction it gives you a unitary quantum mechanics theory, which presumably you would expect quantum gravity to be unitary even in such strange boundary conditions. So.
Where exactly the first part of your lecture will fail for the other sign of lambda?
Yeah, that's a very good question. So it won't fail. So the way that I wrote it, it makes sense for any sign of this cosmological constant lambda. Of course, what you'll see is that if you do the computations for the wrong sign, then you'll get, when you compute the S matrix, instead of getting a time delay, you'll get a time advance. So your S matrix will not be causal because of that wrong sign, but you don't see anything wrong directly in the gravity theory per se.
I can recover the spectrum, the exact spectrum that
Yeah, certainly you can compute throughout the spectrum, and you see these problems also in the spectrum. Again, since we write it as a theory of gravity, it's not obvious that it's going to be unitary in these coordinates x mu and so on. Again, it's the relation between that theory and the original TT-bar deformed theory involves going to these specific space-time coordinates and so on, and the claim is that in those coordinates, it will not be unitary if you choose the wrong sign of this parameter alpha. Yes? So I do not write the black hole, but the idea is that if you look for black holes that obey these modified boundary conditions and compute their energies, then you see that their energies are now given by these formulas. So again, I didn't write. You can imagine just taking some microstate of the black hole, modifying its boundary conditions in this way, and you'll see that it follows these boundary conditions. So let me just end by listing many problems or confusions that I have with this proposal, and that hopefully some of you can understand someday. So there are many issues with trying to make sense out of this. One problem is that from the point of view of the quantum field theory, it's not very nice to just throw away by hand all the states that you don't like. It's, to paraphrase something that Daniel said, it's like taking the hydrogen atom and keeping just the 4th and 17th energy level. It's not something that you can do, and it gives you consistent quantum mechanics, but it's not a nice thing to do, and it doesn't usually give an interesting theory. So from the quantum field theory point of view, it's not clear what it means to just throw away by hand all these states. And in particular, if you do throw away states by hand, then the spectrum that you'll get will not be modular invariant. So we heard in David Kutasov's talk how this spectrum is modular invariant, meaning that even though if it doesn't define a local quantum field theory, it still defines a theory that exists on a torus. But if you just throw away some of the states, then you'll get a theory that does not even have an interpretation as some non-local quantum field theory. So it's not clear exactly what this dual theory would be. Of course, you can always define it just as the quantum mechanical system with this energy spectrum, but that's not a very interesting definition. And the claim is, does it have any more direct definition? A second problem involves putting in boundaries in theories of gravity. So it's not an accident that when we do AdS-CFT, we quantize gravity with a boundary that's infinitely far away, because trying to quantize gravity with boundaries at finite distance is very problematic, or in fact, not even at the level of quantum physics. Already classically, if you just try to put in boundary conditions of this type, then you have problems that were discussed in a recent paper by Edward Witten, if you just try to make sense of constructing classical solutions with these boundary conditions. In the quantum theory, things are even worse, because we expect that any object that you put into a theory of gravity will fluctuate under the gravitational force, and you cannot just put in some fixed boundary and declare that space stops there. Certainly, all the boundaries that we know how to put in string theory or any other consistent quantum theory of gravity that we know are always dynamical fluctuating objects. So it's not clear what it means to just put in a boundary of this type by hand. It's something that we haven't seen before. A third problem is that I described, this change manifestly changes the boundary condition for the graviton, and it does it in a way that's exactly related to the TT bar deformation that we wanted to have. However, if you really put in AdS, so really have this AdS space, and you really now cut it off at some z equals zc, then of course all the other fields that you have living on your space also now just live in this region of z less than zc, so we have to change the boundary conditions for these other fields also to be at z equals zc instead of at infinity. So you're forced to change the boundary conditions also for any other fields that you have in your bulk, of course, or for any reasonable conformal field theory, you'd have extra fields in the bulk and not just this graviton. And if you just follow the same route that we followed for this, then if you have some scalar field phi in the bulk that's dual to some operator O in the conformal field theory, then these modifications would correspond to taking the Lagrangian of our original theory and adding to it, already at leading order, some deformation that looks like O squared. So this is the analog of TT bar. If you have some other scalar field in the bulk, then exactly the same arguments would tell you that you're adding a deformation by that operator squared. And of course, this is bad because, well, for TT bar, we had these very elaborate arguments telling us that that theory was well defined, despite the fact that it's an irrelevant deformation. None of these arguments hold for any other deformation of this type. So these theories, they may be formally well defined at large n, but at finite n, I'm finishing in a minute. For finite n, there's no reason to think that these deformations make sense. And even if one can make sense of them, they're certainly not the same as just the TT bar deformed theories. And a final issue is that what we'd like to do when we do the TT bar deformation is to take our original spectrum and just deform it somehow. But when we put in this cutoff on AdS space, that's not quite what we're doing, because in our original background, there were states that lived also in this region, and in particular, there were even low energy states living in that region, which you would not want to throw away. But still, it's not clear what happens to those states if you just cut off the space. It looks like you just lose them, which again is not consistent with what we expect from the TT bar deformation. So there are lots of open questions about how to interpret this suggestion. And on the other hand, there are some nice pieces of evidence that it makes sense somehow. So I'll leave it as an exercise to the audience to find a way to solve all these problems and find the correct holographic dual for these TT bar deformations.
How much time do you allow?
Until the tutorial in the evening, I'd like somebody to tell me the answers.
Let's make further questions in the tutorial.
Hi everybody, I just wanted to ask you not to leave any bags or laptops in the room because there are a group of high school kids who are coming to their physics lecture in this hall. So just don't leave anything to this Sorry.
Så där.